Hello everybody, in this video we're going to measure the time in microsecond or nanosecond using timer. For example, each instruction, how long does it take? This instruction takes 670 nanosecond. Let's get started with this.
Connect the STM32 ST-Link and connect to the PC, and we open the CubeIDE.
In the CubeIDE, let's create a new project, file, new, STM32 project. For the commercial part number, I put F103C8. This is the one. Next, I put name micro counter. Finish. Let's do the setup. Let's zoom in. And system core, sys, debug serial wire, and RCC. We select the crystal ceramic resonator for the high speed clock, and then clock configuration we change this to 72 megahertz. Enter. Okay. Now the timer clock is here. APB1, APB2, both of them are 72 megahertz. So both are 72. So we go to pinout on configuration. We select the timer. I'm going to choose timer 4. You can choose any timer, and clock source internal clock. And because it's a 72 megahertz, I want to make 1 megahertz. So divide by 72. So we get 1 megahertz. So we can get 1 microsecond from 1 megahertz. And also I'm going to change the PC13 to GPIO output. That's the LEDs connected. Yeah, that's all the setting. You click save to generate code. In the main.c file, user code PV, I'm going to have a variable uint32t, time taken, and in the user code 2, I'm going to start the timer. That is HAL tim base start. This is the one. So we select the timer. That's the timer 4. And in the while loop, first we set the counter to 0, underscore, two underscore, and then HAL tim set counter to HTIM HTIM4 and make it to 0. Now I'm going to measure the hull delay, how long it's going to take the time for hull delay for 1 millisecond. Yeah, 1 millisecond we put it here, and then after this one done, we get the counter is time taken equal underscore HAL tim. Now this is get counter. Again it's a HTIM4. Now what's happening is here is setting to 0, and then after done this function, it takes how much time taken in microsecond. Now we can save. So I'm going to use this button to debug. If it is a clone board, this debug won't work. So use the UART or in a LCD display to display the values. So here I can click OK, because my one is original board. Switch, and go to live expression, and I delete all of them, and I type a new one, that is time taken. Let's see, let's run. It is 1999. So it's nearly 2 milliseconds. So what is happening is here, it's double the time. We supposed to be 1 millisecond, because if you go there, hull delay 1, it's 1 millisecond. It should be 1000, but it is 2000. What's happening here? Let's see. We stop this one. When you go to the micro counter, the counter can go up to 65,000. So it can measure up to 65,000 microsecond. So let's go to the main.c, make it around, say, 60 millisecond. So it's 60,000 microsecond. Let's see, let's save and debug again. Switch. Now run again. So it's 61,000. See, 61,000. It's 1,000 different. So what is the thing is, it's 0 is when you go to the hull delay. Whenever it is 0, that is 1 millisecond. 1 means 2 millisecond. It start from 0. So let's do and see to make sure it's correct. Stop and go to this one. I make it 0. Now hull delay 0 means actually it's 1 millisecond. Let's save and then debug and resume. See, it's 1,000 actually. So that means hull delay means it start from 0. 0 is 1, 1 is 2, 2 is 3, like that. So we found out things that hull delay has a different parameter, that's different timing. We always, for example, if we want a 1,000 millisecond delay, we put 1,000. Actually, we're supposed to put 999, 1,000 minus 1 always, right? So that's one thing. Other thing is, for the microsecond counter, it's working properly. So we set the counter and do the things and get the counter. That's how we calculate the microsecond delay. Now we measure the time for switch on the LED and switch off the LED, how long it does take. So we stop it. Instead of hull delay, I'm going to switch on the LED. So HAL GPIO right pin, that is pin PC13. So pin 13 and we make it maybe 1. Save. Now we're going to measure, we save it. We're going to measure how much time this function takes. Let's debug. Switch. Now when we run, it's 1 or 0. So it's very little. It's around 1 microsecond. So to measure this function, how long does it take? It's not accurate. So what we can do is we put 100 of them like this, and then we divide by 100 to measure the exact time. So what I do is I stop this and I copy this. 199. So it's I put 100 times the right function. Now what we do is I save it and then I debug. Now when we run this, resume this, it's 62 microsecond for 100 writes. There are 100 writes here, 100 of them for 162. So one write one of these function takes 0.62 microsecond or 620 nanosecond. So that's how we can measure. It's very precise. We can measure like that. If we want to measure in nanosecond, in more precisely, what we can do is we stop this one. We go to here. We go here and select the timer. We divide by 72 to make it 1 microsecond, 1 megahertz, 1 microsecond. What we do is we put it here 0. So it counts 72 megahertz times. So it's 72 megahertz. Time is nanosecond. It's around 18 nanosecond or something. I will divide and see. Now we save it. Save. Now we can save all of them. It's the same function. We can choose debug. So when we resume here, it's 4,446 ticks. We'll calculate from here how many nanosecond it took. Similarly, writing 0 takes 612 nanosecond. The register level programming to write pins PC32 is here. This is the code. It takes only 134 nanosecond. Similarly, writing 0, the code is here. It takes only 128 nanosecond. It is more than 4 times faster. So in the future video, I'll make another video how to easily make register level programming. I put the link in somewhere here. Thank you very much for watching. If you have any question, write down in the comment section below. I try to answer as much as I can. Thank you. Bye.